Welcome. In this lesson we are going to talk about how to deal with frictionless inclined planes, and there's a special trick that we're going to use to deal with frictionless inclined planes, and that trick is we are going to rotate our coordinate system, and we're going to do that to make the trig easier on us. So our coordinate system now, instead of going parallel to the ground and perpendicular to the ground for x and y, we are going to do parallel to the ramp and perpendicular to the ramp for x and y. So here is our new rotated coordinate system. And this is x and this is y. And if we have a plane or a wedge or a slope with an angle of inclination of theta, then the trick here is we've actually rotated our coordinate system by that same angle, theta. So the x has been rotated up. The x-axis has been rotated up by that same angle, theta. So now we talk about the positive x direction as being down the ramp. The negative x direction is going to be up the ramp. And our positive y is out of the ramp perpendicular, and negative y is going to be down into the ramp perpendicular. All right, so with this new coordinate system in mind, we now draw the free body diagram for all the forces acting on this orange block that's sitting here in the middle. As always, we have the weight of the block, and the weight of the block goes straight down. All right? We also have the normal force, and the trick here, the normal force always goes perpendicular to the surface. So perpendicular to surface is right here. So in this new coordinate system, our normal force is going straight in the positive y direction, and our weight, mg, is going at some angle. If there is no friction, then these are the only forces that are acting on the box. And the reason the box accelerates down the ramp is because of the x component of the force of gravity. So if we draw in the weight components in terms of our new coordinate systems, x and y, this is mg in the y direction. And over here we've got mg in the x direction. And it's that component, mg in the x direction, that makes the block accelerate down the ramp. Now here's the trick. Since we rotated our coordinate system by an angle of theta, that means this angle right here between the weight vector and the y component of the weight vector is theta, the same angle of inclination of the ramp or the slope. So this is how we're going to find our x component and y components of the weight. So our mg in the y direction, since if we look, that component is the side that's adjacent to theta, that's going to be mg cos theta. And our x component of the weight, mgx, if we take and move that, oh, I can't just move that one vector, I got to move the whole thing. If we take and move the mgx vector down here to complete the triangle, then we see that it is the side opposite the angle theta, and so we end up with mg sine theta for the component of the weight going down the ramp. Some people in some textbooks will call that mgx the force parallel, because it's parallel to the ramp. Some textbooks will call the y component of the weight force perpendicular, because it's perpendicular to the ramp. I'm going to keep with mgx and mgy, or f weight in the x direction, f weight in the y direction. Okay? So now if we throw some numbers in here, and let's say we say that the mass of the block is 10 kilograms, and our ramp is inclined at 15 degrees, then we can actually solve for the acceleration of the block down the ramp. And we're going to do it the same way that we always have done it. We're going to talk about the sum of the forces acting in the x direction, and we're going to talk about the sum of the forces acting in the y direction. We need to think about what's happening to this block. It is accelerating down the ramp. That means down the ramp is in the x direction, so the sum of the forces in the x direction are mass times acceleration. The sum of the forces in the y direction, the block does not accelerate perpendicular to the ramp, into or out of the ramp, so the sum of forces in the y direction is 0. All right, so plugging in or filling in our forces that are acting in the x direction, we see that the only force acting in the x direction is that component of the weight, mgx. So we've got mg sine theta acting down the ramp that's equal to the block's mass times its acceleration. And as for our y forces, we have the normal force going up in the positive y direction, and we have mgy going down. So we can say the normal force minus mg cos theta is equal to 0. In the x equation over here on the left, notice that we have a mass on the left, a mass on the right. They cancel out. The mass of the block really doesn't matter. It doesn't matter if the block is 10 kilograms. So we can solve for, or actually already have solved for, the acceleration of the block down the ramp. The acceleration of the block down the ramp, a, we can actually say a sub x, the acceleration in the x direction, is just g sine theta. And in the absence of any other forces acting up the ramp or down the ramp, which we'll get to, especially when we talk about friction between the ramp and the block, then the acceleration is just a sine theta. Plugging in 15, we can do, g sine theta. Plugging in 15, it's g sine 9.8, g sine 15. So 9.8 times the sine of 15 degrees. We end up with 2.54 meters per second squared. Which totally makes sense. It should be less than 9.8 meters per second squared. We can think about the extreme case where the ramp is inclined at 90 degrees, going straight down, in which case we talk about g sine 90. The sine of 90 is 1, so the acceleration would be 9.8. Hey, it makes sense. If you ever get an acceleration bigger than 9.8, and there's only one force acting going down the ramp, then something is wrong. Okay? Let's take a look at an example problem using this new coordinate system. All right, in this example problem, we're going to use the same numbers we had last time. We've got a mass of 10 kilograms. That would be 10 kilograms. And we have an angle of inclination of 15 degrees. And now I'm going to add in another force going up the ramp. So we're going to say there's a force of 50 newtons pushing the box up the ramp. So drawing our free body diagram, we've got mg going straight down. We have the normal force going perpendicular to the ramp in the positive y direction. And we've got some force pushing up the ramp, parallel to the ramp, at 50 newtons. The question that we want to ask is, what is the acceleration of the block? A equals question mark. And we're not 100% sure right now if the block is actually going to accelerate up the ramp or down the ramp. We need to look at the component of the weight that's going down the ramp, mg in the x direction. If mg in the x direction is bigger than 50, the block's going to accelerate down the ramp. If mg in the x direction is less than 50, the block's going to accelerate up the ramp. And if they're equal, the block's not going to move, or it's going to move with a constant velocity. All right, so we've got mgy, the y component, going down here. Finding the components of the weight in the x direction are the same as they were last time. mgx is going to be mg sine theta, and mgy is going to be mg cos theta. We think about the sum of the forces acting in the x direction and the sum of the forces acting in the y direction. And there may or may not be an acceleration on the x direction. So let's assume that there is and go ahead and say ma. The direction of A is going to tell us if it's accelerating up or down the ramp. And Fy The sum of the forces in the y direction, 0. The box is not accelerating in the y direction. So filling in our forces in the y direction, this time we have our forces in the x direction. This time we have two forces acting in x. We have mg sine theta, and that's going in the positive x direction, and we have 50 newtons going in the negative x direction. That's equal to ma. In terms of the y forces, it's the normal force going up, that's positive, minus mg cos theta. Those are equal to 0. We're solving for the acceleration here, so we can divide both sides by m in our x equation, and we end up with g times the sine of theta minus 50 over m is equal to the acceleration. Plugging in numbers here, we have 9.8 times the sine of 15 minus 50 divided by 10 kilograms, the mass of m. That's equal to the acceleration. Plugging this into our calculator, we see 9.8 sine of 15 is equal to 2.54, which is the answer from our last problem, since we're using the same numbers, minus 5 is equal to A. So 2.54 minus 5, we end up with negative 2.46 meters per second squared is equal to our box's acceleration. So A is going that way at 2.46 meters per second squared. So what that means to us is, assuming the box was initially at rest, the box is going to be accelerating up the ramp at 2.46 meters per second squared. If the box was moving down the ramp, then that means that the box is going to be moving down the ramp and slowing down until it comes to a stop. Then it'll reverse direction and go back up the ramp. So it all depends on what the initial velocity of the box was. Assuming it's at rest, the box is going to accelerate up the ramp. All right, so the keys, again, for these are understanding that this angle here is theta once we've rotated our coordinate system. And we rotate our coordinate system so that x is now parallel to the ramp, y is perpendicular to the ramp, and it does, believe it or not, make the math easier, because then we only have to find the components of the weight vector. If we didn't rotate our coordinate system, then we would have to find the components of the 50 Newton vector and the normal force in the x and y direction. So it does make it easier. So rotate your coordinate system, use that angle theta right there between mgy and mg, and solve the problem like we always have. Sum of the forces in the x and the sum of the forces in y. Plug in the forces, solve for the unknown. I'll see you guys later.